All right, so let's take a deeper look at ionic compounds in particular. So this first slide just kind of summarizes what we had talked about in the last video. So as a reminder, in ionic bonding, there is a really strongly attractive atom or group of atoms, and what they do is they're so strong that they completely pull an electron away from a more weakly attractive atom, and that causes two different ions to form, the cation and the anion. And generally, because metals have the weaker attraction, the metals are going to form the cation after losing an electron, whereas the nonmetals will form the anion. These two oppositely charged atoms then attract to each other according to Coulomb's law. So all of the rules we learned before about the larger the charge or the smaller the distance, all of those things apply to the ions as well. And that attractive force between the two, that is what we call an ionic bond. So when we have an ionic compound, their structure is very different from what we think of when we look at covalent compounds or things like water and carbon dioxide. So if we take a look at what that means, two things we have to keep in mind is that ionic compounds are always going to become overall electrically neutral, meaning that the number of positive and negative ions in that overall ion structure are going to cancel each other out. And they're going to do this by forming a crystal lattice, similar to what we were doing with growing the crystals for the lab. So if we look at our example of sodium chloride, right, our normal table salt, we have sodium metal here on the left, we have chlorine gas here on the right. So if this was a piece of sodium metal over here, like the sodium that was dropped into the water for the metal reactivity lab, we know that since the sodium has a weak attraction for that electron and the chlorine is much stronger, the chlorine atoms can pull electrons in to fill their octets. And we see that each of these chlorines can gain one electron, each of these sodiums can give up one electron. And what we're going to have as a result is 6 different cations are going to form, and 6 different anions are going to form. So after those transfers happen, we're going to be left with a sodium cation, and we're going to also form a chlorine anion. And now those two oppositely charged ions are going to attract towards each other. Now, in the same container, same vessel that this reaction was happening, there are a total of 6 sodiums and 6 chlorines, and all of those things are now ionized. So this unit that we just made here is not going to be the end of it, because those positives and negatives are going to continue to attract until all of those compounds have been used up. So if our positive sodium attracted to our negative chlorine here, then this positive sodium ion here can pull in or attract to another chlorine ion. And those two negative sodium chlorine ions can attract another sodium cation. And this process is going to continue until all of those different ions are used up. And what we see is that this continues on and on and on until we run out of ions. We're alternating here, right, positives and negatives, because those opposites attract to each other. If 2 sodium ions were next to each other, those would be repulsive. And I drew way more than 6. Oh, not yet. Right, so here we have now the crystal structure of sodium. Right? We see that it ends up forming this nice square. So if you've ever seen salt crystals form, they do form these nice cubes, and part of it is because of the way that these ions pack together like this. Now, for the sake of writing the formula, though, if we were to write the entire thing that is bound together here, we would have Na6Cl6, because we have 6 sodiums and 6 chlorines. But really, if we even talked about a normal table salt, like the amount that we use either in food or during a chemical reaction, we would have billions and billions and billions of those different atoms, and that becomes impractical to write. So what we want to do is focus on just what is the repeating unit, what we call the formula unit of the ionic crystal. And this crystal is formed in this case by the repetition of this sodium and chlorine pair. Right? There are 6 of those pairs in this crystal, and it's that pair that makes an electrically neutral compound where we have the one positive and the one negative canceling out. So the formula that we write for sodium chloride is just NaCl with 1 sodium, 1 chlorine, and in this case we have 6 of them, so that's what those numbers in front represent. It's how many of those units. Right? The unit itself, 1 sodium, 1 chlorine, but 6 of those units are present. If we look at magnesium and chlorine, right, it's a little bit different because unlike sodium, magnesium has 2 valence electrons. So if we were looking at the same thing that's going on in terms of the transfer of electrons, each of these chlorines can pull in 1 more electron again. So we see that 1 of these electrons will get pulled by chlorine, but magnesium is still going to lose this second valence electron. However, it cannot go to the same chlorine atom because there's no room for it. It would go to another shell, and that's just not a strong enough attraction. So that second valence electron actually gets taken by a different chlorine atom. The same process is going to continue until we are unable to continue the process any longer. And what I see here is that when this transfer starts to occur, I'm going to be left with a magnesium cation that now has a positive 2 charge because it lost 2 valence electrons. And my chlorine atom, well, each of those are going to be filled, but in order to take away those 2 electrons, 1 chlorine gained 1 electron, and a second chlorine gained another electron. So we have 2 different ions here. We have the magnesium with a positive 2, and we have 2 of the chlorine ions, which is represented by the small number 2 in the formula here, right? 2 of those things. And based on the arrow diagram that we drew down here, we can see that in order for this to go to completion, I would need to use 3 magnesium ions, or atoms. And as a result, in order for those 3 magnesiums to give up all their electrons, I would need 6 chlorine ions. I'm using the brackets here around the ions to show that these chlorines have that -1 charge after the gain of that extra electron. So we have all 3 magnesiums drawn. 1, 2, 3, 4, 5, 6 chlorine ions. And what we see is that the structure of this is going to look a lot different than that of sodium chloride with its nice 1-to-1 ratio, because we don't really end up with a cube here as those different ions stack in more stable states where the negatives don't go really next to the other negatives. But to form this crystal, again, it's made up of a repeating unit. And in this case, the repeating unit, the formula unit, is 1 magnesium for every 2 chlorines. So the formula we write for this compound is MgCl2. Again, that little 2 represents the number of chlorine ions. And we have 3 of those units in this crystal. In this case, the 3 magnesium atoms over here that weren't involved, those would just remain magnesium metal at the bottom of the container, right? They didn't react, they didn't undergo anything because there's nothing to take the electrons away.